record. Okay. আচ্ছা, বোর্ডটা ক্লিয়ারলি দেখা যাচ্ছে? ওকে, দেখা যায়। তো আজকে আমরা যেটা দেখবো সেটা হচ্ছে মলিকুলার স্পেকট্রোস্কোপির সেকেন্ড পার্ট, যেটা দ্যাট ইজ ভাইব্রেশনাল স্পেকট্রা অফ মলিকুলস। ওকে, তো আমরা মোটামুটি ভাবে in the very first lecture we have seen that molecules have several kinds of energy: rotational energy, vibrational energy, and translational energy. And we have also learned that the being very high, the translational energy being very high, it gives a continuous energy spectrum, and that doesn't lead to any kind of discrete spectrum to be generally observed in the laboratory through spectroscopy, etc. Or it doesn't give any kind of in-depth structure of the molecules. So we are interested to investigate the various aspects of rotational and vibrational spectra. And in the last three classes, I have discussed about the rotational spectra of molecules. And now, today I shall discuss about the vibrational spectra of molecules. So, vibration means, suppose if we talk about diatomic molecules, then it has two atoms. So one atom is here and another atom is here. They are bounded by some bond, and this bond may be an ionic bond, or maybe covalent bond, or it may be metallic bond, or any other else, or van der Waals bonds, or any other else. But whatever be, these atoms actually do not remains remains fixed in space. They actually vibrate about their mean position. So whenever we talk about the position of atoms in molecules or atoms in solids, we basically mean to denote the equilibrium position. So about their equilibrium position, they vibrate, and this vibration have some energy. To study this vibrational energy of molecules, so let us first discuss about the vibrational energy of any oscillator. The most simplest case we have studied that the spring is there and we have a mass, right? A mass, it's oscillating like this way, and the spring has spring constant K. So in this case, we can write the equation of motion as m into d2x dt2 equal to minus k. So sometimes this k is a spring constant. So from here we write this h double dot equal to h double dot plus k by m into x equal to 0, and this is termed as the natural frequency, that is the omega 0 square we take. So what we get is omega 0 equal to root k by m, and that is equal to by nu 0. So the frequency nu 0 we write 1 by twice by over k over m. So this is actually the frequency of a simple one-dimensional simple harmonic oscillator, where a mass oscillates in attachment with a spring whose one end is fixed to some base, right? Now, in the case of molecules, the situation is quite different, because in case of molecules, you have two atoms. So this is atom A, and we have another atom B, and now they are bounded by this one. So in this case, what we take these as a harmonic oscillator of single mass with the reduced mass m as m1, m2, m as m1, m2 by this m1 plus m2, right? So this is the reduced mass of the system, and in this case, this motion can be described by one-dimensional problem of single mass, and in this case the frequency of oscillations will be mu0 will be just the same as like the previous one. So this is 1 over 2 pi root k by, instead of m, now we shall use the reduced mass of the system mu. And you have already done the quantum oscillator. You have already did a lot of mathematics and physics of one-dimensional simple harmonic oscillator in quantum mechanics also. And in quantum mechanics, you see that the energy spectrum of such a one-dimensional oscillator is quantized or discrete, and the energy spectrum is usually given by EV equal to this B plus half to H mu 0. In quantum mechanics, we use actually n there as the quantum number here. Since this is vibrational, so this V is known as the vibrational quantum number. And this V runs from 0, 1, 2, 3, and so on, all integers. Right. Now in spectroscopy, as you have also mentioned earlier, that it's very much convenient to express this energy in terms of the wave number. So what we do, we divide this energy by hc, so it becomes 1 by lambda. That is, we can write that v, this will be v plus half, and since we divide by hc, this will be into mu 0 by c. Okay? So this is the v equal to this v plus half into mu 0 bar. So this is the general equation for the wave number for one-dimensional harmonic oscillator, and this is usually expressed in centimeter inverse. That is the common method we use. So this is usually expressed in centimeter inverse, right? Not centimeter, I think. This is centimeter inverse. Okay. Okay. So if we take V equal to 0, that corresponds to the ground state of the oscillator or the ground state of the molecular vibration, and it has energy. Then this E0, we can write this is half mu 0 bar centimeter inverse. So this is the ground state energy of that oscillator, which is sometimes called the 0-point energy, and you have already learned all these things, right? I think some writings are there, so this should be okay. Now, what is the difference in the quantum harmonic oscillators, one-dimensional simple harmonic oscillators, and in molecular oscillators? Because while solving the one-dimensional harmonic oscillator problem, we took the potential energy. If we take one dimension, Vx equal to half m omega naught square. Okay, so this was the potential energy. But in this case, the situation is quite different. The potential energy is doesn't follow this kind of behavior. If you took this kind of behavior, then what will be the potential energy curve? If we have this is x, this is positive x, this is negative x, and we plot v versus x, we have a potential energy curve like this. Okay, so this is the potential energy curve. But now in molecular vibration, the potential energy curve is quite different, and the potential energy is given by an equation which is basically known as Morse equation. I'm writing the part, or sometimes this is called the Morse potential. Morse potential. So, how will be the potential? The potential is actually expressed as this U. I am writing this as U. So this U of R E into 1 minus exponential of K into R minus RE square, I think. End up here, here, and here. Okay. So this is the general potential form. I think the square is now, so this is the square, right? So this is the general form of the Morse potential. What are the factors? This D? This D is known as the dissociation energy. Dissociation energy required to dissociate the atoms from the molecules, and this A is a constant. This in fact, this is a constant for a particular type of molecule, and this is different for different molecule. And another term is there. This Re. This Re is actually the internuclear distance, which corresponds to U equal to 0. So this is the its internuclear distance when U of R equal to 0. Okay, so this is the potential, and this is actually given by P and Morse. That's why this is called Morse potential. And now let's see how the potential looks like. If you see, the potential will be like this way. This is the general form of the potential. Okay, so what you see over here, that instead the earlier case that you have seen, the potential was parabolic like this way, and it goes like this. This is the case of V equal to, or here I say U equal to half m omega 0 square x square, and now the potential takes the forms like this. So this is the actual deviation from general harmonic potential. So in fact, you can also take this potential, take in one dimension, instead of R, put a X, and then you put in the potential function, and then you can uh, solve the Schrodinger equation using this potential as a perturbation, and then you can also calculate the energy levels of various states. Okay, so this was the basically Morse potential for a diatomic molecule. If the molecular structure is different, then this potential becomes quite complicated. So I'm not going into details. We shall be limited to only diatomic molecules, so that this simplified Morse function can be used. So now the oscillator, instead of harmonic, these enharmonicities are there, and due to this enharmonicity, the energy spectrum will be changed. Okay. So the data energy spectrum will be changed. Okay. So now what will be the energy for these enharmonic oscillators? So on solving Schrodinger equation, what we get, that earlier we have the energy equation, this V equal to V plus half mu U1. Okay. Earlier I wrote it as mu 0. Now I am writing this is a mu E, because this is the case of enharmonicity. Okay, this is mu E bar. Okay. And now there will be some additional contribution due to this enharmonicity, due to this Morse potential. So what are the factors? That factors will be this V plus square V bar into pi E, this term. And there will be other term like V plus of cube is a YE newer, and so on and so forth, like that, where then this V runs from 0, 1, 2, 3, and so on, right? Okay, so this is the case of this enharmonic oscillator under Morse condition. So now here we found two more constant. One is this chi e, and there is this ye, right? These chi e and ye, these are nothing but the enharmonicity constant. Enharmonicity. That's chi e. These are basically enharmonicity constant, and they play a crucial role in determining the energy states of vibrating system. This is different for different molecules because types of vibration and the molecular structures are different. That means the symmetry is different, so that the vibration will be different. Obviously, this mu, this chi e and ye will be different. Okay. So in our study, we shall consider only up to this first order correction term. So we shall take the energy form up to this way. So the energy spectrum. So before going into the details of the spectrum, if we talk about the simple one-dimensional harmonic oscillator, in that case, what we have? We have this V equal to, this is V plus half into mu 0 bar. So what are the energy levels? So this corresponds to V equal to 0, and then so this energy is half mu 0 bar. Then how much? 3 by 2 mu 0 bar. Then 5 by 2 mu 0 bar, and so on and so forth. And the condition was that this delta V will be plus minus 1. This was the selection rule for transition. So we have the transitions like this, or this, or this. So whatever we do have, we always have a single frequency, because this is how much? Mu 0 bar. This is mu 0 bar. This is mu 0 bar. So in the absorption band, we get a single frequency of mu 0 bar. That was the case of general simple harmonic oscillators, but in the enharmonicity is included, the situations are quite different. So now we have to find this energy level. So before going into that, there are several criteria and selection rules. We shall first discuss about that, and then we shall go to plot these equations. Okay, let's see. So we have the energy term as V equal to V plus half bar. Sometimes my nu and gamma becomes identical. So here no scope of gamma is there. So whenever it's like gamma, they just take it as nu plus of a square bar by once. Okay. So this was the formula, and this chi is always positive. Okay, this anonymity. What is the effect of this anonymity? This anonymity basically is the crowding of the level. So you see, in case of harmonic oscillator, one dimensional simple harmonic oscillator, the energy levels are equispaced. The gap is same. But due to this anonymity, you see the energy levels become crowded. If you see here, if you go for higher values, you see that these energy levels are now crowded. In this region, you see the energy gap changes. So energy levels gets quite crowded, right? That is the effect of the enharmonicity on the oscillator. In this enharmonic system, that the energy levels becomes crowded, and that is how much crowded the levels will be. That will be determined by this term, this chi. Okay. Okay. So now, if we write this V plus 1, you can take a paper and pen, and you can also calculate with me. So this EV plus 1 will be how much? So this will be V plus 1 plus half, that is V3 by 2 V bar minus V plus 3 by 2 square V bar and chi. And if we take the absorption from this V to V plus 1 level, then what we have is that V plus 1 minus EV. So how much it will be? This V square. So this will be 1 3 by 2 3 by 2 square. That will be, I mean, nu bar minus 3 9 by 4 or 2 into 3 6. That is by Then so this will be 2 pi e mu bar into v plus 1. This is in second term. So this is the equation, governing equation, and this equation you have to remember because you have to calculate the energy band. So you have to remember this formula. This gives you the energy levels for transiting from B to B plus 1. And if we calculate the exact 0 point energy, right? If we calculate the exact 0 point energy from this equation, we put D equal to 0. So how much will be the 0 point energy? This is if we put V equal to 0 over here, this will be half mu bar minus 1/4 mu bar by E. So if we take a half common, so 1 minus half by E. And you see, if this was a real harmonic oscillator, one dimensional simple harmonic oscillator, in that case, obviously you can see that this term, this anomalous will be absent in case of harmonic oscillator. Then this is half U E bar. That is exactly matches well. So we can write that previous equation, that this one, I mean that right this way. You can take this V plus half common. Take this V plus half and U bar common, then 1 minus V plus half U bar pi. So how much it will, how it will look like? It will look like this V equal to, we are taking V plus half as common and U bar as common. I'll write it at the last. So this will be half, sorry, 1 minus this V plus 1 square, V plus half square, that is V plus half into this square. And U bar is obviously there. So this is also another form. And equate this equation with the case of one dimensional simple harmonic oscillator. In one dimensional oscillator, what do you have harmonic case? This will be V plus half U0 bar. That was the case of harmonic, and this is the case of anharmonic. Like, okay, so we compare. If we equate these two equations, then what we if we assume that these two energies are equal, then what we get? This we get this nu zero as this one times nu e. So we have this nu bar equal to nu bar, nu bar equal to nu bar into 1 minus v plus half. So if we replace the nu zero by this equation, then the entire enharmonic vibration can be treated with the harmonic vibration. Just we have to replace nu zero by this one. Okay. Now, if we practically see the transition levels, transitions between various vibration levels, then it falls in the region 50 to 400 centimeter inverse. That is the entire infrared bands, or there are some Raman bands and other absorptions are also there. That range is basically from 50 to, I think, about just this is not exact value, but range. Inverse like that. So now let's get into more into the infrared spectrum. So this is where the vibrational status. Now we shall discuss in details about the infrared spectrum. So as you know that these molecules have different types of atoms, and their structures are different. So the vibration obviously will be different. The vibration nature of different molecules will be different. Okay. So energy of most of this molecular vibration is obviously quantized because these are basically quantum states, and this energy corresponds to the lies in the infrared region of the electromagnetic spectrum. So whenever any infrared radiation of same frequency is incident on the molecular system will absorb the energy, okay, and it causes excitation to the molecules, the higher energy levels. Okay, suppose a molecule is in this state, right? And although I'm writing this as atom, suppose this is a molecule, it is in this state, and say this is V equal to 0 and this is V equal to 1. Right, this is V equal to 1. Now, if the energy of the external electromagnetic radiation is such that it's exactly equals to this, then this molecule is excited over here. Okay. The molecules absorbing this energy gives rise to the absorption band, which basically lies mostly in most of the cases. It is found that it lies in 200 to 4,000 centimeter inverse region. So this is completely in the infrared region of the electromagnetic spectrum. Also, there are organic molecules. You see several functional groups. They also have these vibrational frequency characteristics. And by studying this absorption band or these vibrational frequencies, the type of functional groups can also be identified. Okay. So these was infrared spectra, and with time there are lots of developments in the infrared spectrometer, and it can cover. So although this is the range now, the modern infrared spectrometer that can cover from 50 to 12,500 above this one centimeter inverse. In this entire range, it can cover. So this region is actually subdivided into different regions. The first one, if we say, actually we shall write from this way to this way. So this 12,500 to 4,000. Okay, they are all writing in centimeter inverse. This region is known as the near IR, near infrared region. And from this 4,000 to 400, this region, this is actually called mid IR region, mid infrared region, and this 400 to 50, this one, this is known as the far infrared region. So we found these three types of infrared region: near infrared, mid infrared, and the far infrared region. And the middle infrared region is the mostly used for standard laboratory characterization of various types of molecules. Basically, most of the molecules shows transitions in this mid-infrared region, that is 400 to 4,000 that I was mentioned around this region. In most of the molecules shows absorption bands. So most of the spectrometers are devised to operate in these wave numbers. If we study below this 400, and if we go to far higher region, in that case we have used some special attachment to the device to characterize to study this far higher, and that is very much very rare. There are only few samples that actually exhibit this far higher. So these are basically regions of spectrum of infrared bands. Okay. Now we have studied the vibrational energy levels. So what are the selection rules, or what are the conditions that to be followed for a possible transition? The necessary condition for absorption of a quantum radiation photons Hν by the molecule must be equal to the energy. Let us represent the two states as say psi I. This is one state, and the state. So these are the two states involved. So their energy, say this is I, and this is J, the energy states. To absorb the radiation frequency must be exactly matched with the energy difference for this, right? That is a very common emission or absorption rules that you know. And this transition between the states influenced by the external electromagnetic radiation will depends on how the electromagnetic radiation interacts with the electric field with the dipole moment. That means the electric field of the electromagnetic radiation and the electric dipole interaction of the molecule. And if you go back to your, to the quantum theory of molecular system, that is actually out of scope of the syllabus. In that case, we get a probability of transition from any from this ith state to this jth state is actually given. If we write this, first, it's mu ij, which is the say psi star mu ij. That is, mu is basically the operator corresponds to dipole moment of the molecule, and this has to be finite for the molecular transition to happen. And again, this dipole moment of a molecule is basically the function of the normal coordinates of the vibrational mode, because you have read about the vibrational modes of normal coordinates. You learn classical mechanics about the vibration of linear, there. All those generalized coordinates were reduced to normal coordinates. Okay, and this dipole moment the operator obviously depends on this normal coordinate. And if we expand this dipole moment Taylor series, what we have in that case, you can write that this mu will be mu0 plus del mu del qk, or we simply write it as qk. Okay, this is usually simply write it as qk, and so on and so forth. So this is simply Taylor series expansion of this, and we are considering here only the up to this first order term, we are neglecting the higher order term. So if we put this mu value over this one, what I get the probability transition and the dipole moment, this mu ij will we have to put here. So this is integral first term psi ij mu0 psi j. So this is psi I star mu0 psi j d term, the first term, and the second term is del mu del qk integral psi I star the normal coordinate change like here. So this one. Okay, and this mu has a constant value, so you can take it out over here. So now, so then how will this term will look like? So this term will look like this. Let's wait for a few minutes because there is a lot of noise. Just wait for a minute. We will stop. Let me write something in between. Okay. So if we look at this first term, and since these two states are different, then what orthogonality condition says? So orthogonality condition says this first term must be, okay? And we shall have only this second. So let us look at the second term. Okay. So mu to survive, the second term has to survive. Second term, that means this is getting the q k. This should be finite. Okay. So let us write about the origin. Okay. This must has to be known. And dipole moment of the three if we use ordinary say Cartesian or not Cartesian, here we use normal coordinates. Then obviously you see that there are several components of the dipole moment. At least one component of mu has to survive. Okay, so that we give it will give this mu ij not equal to 0. So that is the condition for a molecule to exhibit the vibrational spectrum, or so that it will become ultra-reductive. So at least one component of this del mu del Q will survive. So the vibrational motion must give rise to a change in dipole. So that is the change in dipole moment with respect to normal coordinate. So it has to be finite and non. So this is the condition for a molecule to exhibit two vibrational spectra. Okay. And also the integral, because the integral what we wrote that was del mu del q k 0 integral psi I star k psi I deta. Actually, that was the second term that we get in because the first term was 0 orthogonality condition. This also this has to be finite because this also has to be finite and this one has to be finite, and this will survive. This term will survive only if delta V becomes plus minus 1 for harmonic approximation. If you consider the motion to be harmonic, this, as this delta V change should be plus minus 1. And if this is anharmonic, it should be plus minus 1, plus minus 2, and so on. Anharmonic. Since we are taking this anharmonic case, we have to consider this. Earlier, I have already shown the spectrum that for harmonic case, you have only one frequency because that in that case, the delta V was plus minus 1. Okay. So this is the condition, and now let us look into the vibrational spectra of a diatomic molecule. So let us write the equation again. So let us write the equation first. We shall write this under the harmonic approximation. So harmonic approximation, what was the equation? This EV was right. So this was the case of harmonic motion, not the harmonic approximation. So if a molecule makes transition from say V equal to 1, not V equal to 1, from V, not writing this way, from V to V plus 1 state. If a molecule jumps from this V to V plus 1 state, so what will be the wave number? We have this V plus 1, this will be V plus 3 by 2 nu 0, and EV already we have, so this nu bar will be EV plus 1 minus v, that will be this plus 3 by 2 to the power minus plus half to the power. So whatever be the transition, all transitions will lead to the same sequence that I already told, that all transitions will have only a single frequency. Now, if the anharmonicity is taken into, because here we have this delta V equal to plus minus 1. Now, if you go to anharmonicity, then the situation is different, because there are the selection rules are delta V equal to plus minus 1, plus minus 2, plus minus 3, and so on and so forth. Okay. So, how it will look like? So, let us write the anharmonic equation first. So, how was the anharmonic equation? Just write it over there. So, V was V plus half V bar minus V plus half square V bar to chi e. This is centimeters. So this was the equation. Now we have to put different transition levels. Suppose a molecule transits from V equal to 0 to V equal to 1 step. Okay. So how much will be the new? So if the frequency be new, I'm writing the 0 to 1 whole number. This, so this will be equal to basically plus 1 minus. So how much it will be? If we take, no, sorry, not like that. It will be E1 minus E0, because we are taking from 1 to 0. So if we put 1 in this equation, how it will be? This is 3 by 2 nu e bar minus 3 by 2 square nu e bar pi minus this is E0. E0, now we have to put 0 in this equation. So this will be half nu e bar plus half square nu e bar pi. So this is nu e bar minus 3 fourth plus 1 fourth, that is minus 2 basically. But this will be 1 minus 2 chi e bar. So this is the frequency of transition from V equal to 0 to V equal to 1 step. So we have 2 steps. So this is V equal to 0, V equal to 1. This is the transition. This is mu 0 to 1. So this is the case, right? So we can. So this is what is called the fundamental absorption. It's called fundamental. Now, if you write, it will take mu 0 to 2. How it will look like? So we take 0 to 2. How much it will be? Now if you put 2 over there, so this will be 2 plus half v bar minus 2 plus square v bar pi minus this 0. It will be half v bar minus, that is plus square v bar. So this will be 3 by 2 minus half. Oh, no, sorry. 5 by 2 minus half, that is 2. 2 nu bar minus, this is 2 divided by 4 minus 1/4, that is 6. Right? So this will be 6 nu bar. So you can take common this 2 nu bar, 1 minus 2 chi. This is what is called the first overtone. It is called the first overtone. If you calculate v equal to 0 to v equal to now 3, this will be now called the second overtone, then third overtone, and so on. So these are the energy spectrum of various levels. So let me show you the energy levels over here. Can you all hear me properly and see the screen? Okay. So exclude this part. Don't look into this part. Okay. So we shall discuss only up to this part. So these are the various energy levels. So we are taking as this v equal to 0, v equal to 1, v equal to 2, 3, and so on. And you see the transition, this transition from 0 to 1, 0 to 2, 0 to 3, 0 to 4, and so on. So this 0 to 1 leads to this fundamental, 0 to 2, that is first overtone, second overtone, and third overtone, and so on. There are so many transitions are there. So these are the actual shows the absorption bands of this vibrational levels of these molecules. But in all these cases, we have considered only the transition from v equal to 0 state. That means from the ground state, from v equal to 0 to v equal to 1, v equal to 2, v equal to 3, and so on. That means the overtones are there. Then, what about the state if a molecule jumps from, say, v equal to 1 to 2, or v equal to 2 to 3, 2 to 4, etc. So let's discuss that. So if we write molecule jumps from v equal to say 1 to v equal to 1 to v equal to 2 state. In this case, how much frequency will be? It should be 2 plus half millibar minus 2 plus half its square millibar chi e minus. Now we have to put this one. So 1 plus half millibar minus also plus 1 plus half square bar. Okay. So they do a little bit of calculation. So 5 by 2 minus 3 by 2, that is 1. 5 by 2 by 25 minus 1 by 2, or 4. 4 means 4, 16, 4. So this will be 1 minus 4 chi e into millibar centimeter inverse. Okay. So this was the case of transition from v equal to 1 to v equal to 2 states. Okay. Now you see this value. This is 1 minus 4 chi, right? So where it will this is 1 minus 4 chi. If you look over here close to this, because this chi is already very small, so this is very 1 minus 3 chi for first overtone, and for fundamental this is 1 minus 2 chi. That means these are very close to these original bands. Okay, so that they cannot be identifications with their identifications are difficult. And second thing is there because you know the distribution of molecules, thermal distribution of molecules among different energy levels obeys the Boltzmann distribution. That is n equal to n0 or minus this V by kg. So higher the energy levels, lower is the molecules. Okay. So compared to this ground state, the first exercise, so this is V equal to 0 state. In V equal to 1 state, the molecule will be only 0.01% of this N0, right? That means basically what I'm writing is N1 will be 0.01% of N2. What it means? That means the number of molecules in the higher state are very much less, very small. Okay. So even if the transition occurs from this V equal to 1 to 2 states or 1 to 3 states, that energy will be transition will be very small because very less number of molecules will be involved. If we make a calculation, suppose we have 10,000 molecules in the ground state, what will be in N1? It will be 0.10 to the 4. That means only one atom will be there in the n equal to 1 state. So out of this 10,000 transition, if we take say this is V equal to 1, V equal to 2, V equal to 3, sorry, and this is V equal to 0. Here is only 10,000 molecules. If we take that at least 50% makes a transition, so 50,000 5,000 molecules will transit from 0 to 1, and here only one molecule is there. So this transition probability is very less, so that these are the intensity is very small. So when to observe these bands? When the number of molecules in the higher state will be large if we increase the temperature. If we increase the temperature, the molecules will be large in this state. I mean this n equal to 1 state or n equal to 2 state. Then it will occur only at higher temperature. And in that case, these absorption intensities will be observable. That's why these are usually termed as hot bands. These are usually not observed and observed at high temperature only. Okay, that's why it is. These are mostly known as the hot bands. So this is the case of pure vibration of the molecules. That means we are considering the molecules vibrating, but it's not rotating. Okay, it's a pure vibrational energy bands of the molecules. But in practice, the molecules rotates as well as vibrates. So the molecules have both kinds of energies. Okay? Both the rotational energy and the vibrational energy. So in that case, the total energy will be the rotational plus vibrational. The rotational, this will be Bj into j plus 1 minus d j square into j plus 1 square. Plus, we take this vibrational energy, this will be this d plus half dv bar minus d plus half square dv bar chi e. Now we have to consider all these rotational levels and vibrational levels. Okay, and I shall discuss in details of this both rotational and vibrational bands in the next lecture. I shall end up here. Only the pure vibrational motion of the molecules. So, if you have any questions, you are free to ask. If you have any questions, work 3 to work. Okay.
বলছি ওখানে যে অর্থোগোনাল যে কন্ডিশনটা লাগানো হলো সিস্টেমটা সবটা অর্থোগোনাল হবে এটা কি করে বুঝতে পারবো?
কারণ অর্থোগোনাল মানে আমাদের দুটো ডিফারেন্ট স্টেট, একটা v equal to 1 স্টেট, v equal to 1 v equal to say 1 আর v equal to 2, এই দুটো অবশ্যই মিউচুয়ালি এক্সক্লুসিভ হতেই হবে। কারণ একটা মলিকিউল, একটা সেম মলিকিউল ট্রানজিট হচ্ছে ফ্রম ওয়ান লেভেল টু অ্যানাদার, তাহলে মলিকিউলটা দুটো লেভেলে অ্যাট এ টাইম থাকতে পারবে না, তাই না? কারণ ওটা আমি যদি একটা মলিকুলার রেফারেন্সেই দেখছি, তো যে একটা মলিকুল v equal to 0 থেকে v equal to 1 এ যাচ্ছে, ঠিক আছে? আর কিছু বুঝি একবার আনমিউট করেছিল কি বলবে বলে, কি হলো? আচ্ছা আচ্ছা, আর কিছু কোশ্চেন আছে? অ্যাসাইনমেন্ট গুলো সব, হ্যাঁ বল। অ্যাসাইনমেন্ট গুলো সবাই ইন ডিউ টাইম সাবমিট করে দেবি। হ্যাঁ, কোনগুলো দিবি? সেকেন্ড সেমিস্টারে পরীক্ষা দিবি, সিম্পল, এটা সহজ সমাধান, তাই না? এখন যেটা অ্যাজ পার অর্ডার সেটা তো হয়েছে মূলত এর জন্য, কি বলে, আমার এন্ট্রান্স না, মানে ফাইনাল সেমিস্টার, যাদের ফাইনাল ইয়ার তাদের জন্য। তাহলে বাকিদের ক্ষেত্রে কি হবে সেটা বলা যাচ্ছে।